Okay, a couple of things. One, a quick review because I loaded this list of crap. Sorry, where did my picture go? I sent it to me. Oh, heavens. No, I didn't get sent. Well, I'll find it. That's crazy. That is just crazy. Well, it's a construct. I'll go over the brain thing and the construct, and rather than waste time, I can find it and put it up on Wednesday. So I had sent you this copies of that. Nervous system stuff. What I find, okay, it's as I look through questions and I look through aspects of it, what's clear to me is they are looking for, again, they're looking for basic knowledge. Intricacies of the nervous system, not. So, and some of the stuff I really can't work with you with regard to, when they're talking about voltages and all that stuff and the Nernst equation. It's been a long time, 50 years, and I didn't like it then. And, I don't want to do physics, but they really emphasized a lot of stuff. And the reason I picked this, even though we had done this not that terribly long ago, was to be able to get you up to speed. And I don't know, Lindsay, how up to speed are you with nervous system and stuff like
Well, we just reviewed some of it in some lab.
that? Okay, what were you doing?
We talked specifically about like the process of like organization.
Okay.
And, like basic structure.
Good. And then, thanks. So that's kind of where we are with this. So all of this, I mean, the nerve. Okay, they framed it nicely because you have the nervous system for very rapid. You have the because these are control systems. You have the endocrine system for, relatively speaking, slow, hardly slow, but compared to the nervous system, slow. And they did mention the paracrine system, which are these local chemicals that are released first, like playing a pivotal role in inflammation. I mean, they're sort of in between. So that was the first thing as I read through this and I looked at some of the questions that were sent. I wanted to frame it this way, right? For us to sort of talk through it. That was part of it. So, yeah, it's the whole functionality is about the nerve itself. So understanding the basics of the basic composition of the nerve is important. Understanding, and they had some information about the channels when we had talked about depolarization and repolarization. Why? I mean, when you look at the animations, you first you have the sodium voltage gated channels, then you have the potassium voltage gated channels. Okay. The reality is they're so close together. Why would the sodiums go first and then potassiums? Well, the interesting thing, the sodium ones are much more sensitive to depolarization. It's not magic. It's not spatial positioning along the nerve. It's sensitivity. Okay, there's all these little interesting nuances that I was seeing where, and to me, what I'm thinking, even if you just remember some of the basics, particularly for questions when you're stuck having to guess, and maybe you've been fortunate enough to do process of elimination, you know, that's the little stuff that in the back of your mind I think helps you more than anything else. So here again, there's chemistry and physics and characteristics. What I had wanted to cook up, and I'll do it next time. Because I'm being lazy, was to understand the roles of parts of the brain, and that was what sort of triggered me to doing this. Was this first thing that's here? So, a view of the chemistry and physics of the neuron. Okay, that's what we're going to talk about a little bit. Okay, they're talking about biological and physical principles. We'll just do the biological interactions, conversion of information, electrical and chemical neurotransmitters. Fine. And so, following major divisions of the nervous system, that's coming. So maybe it's better framed on Wednesday to understand what you. And so here they immediately said this is you can't see it obviously from this, the hippocampus. The hippocampus is the area where we formulate memory more than anything else. So it basically cements our short-term memory. You might recall that's where Alzheimer's patients are typically affected by problems in the hippocampus, because it affects their short-term memory and it funnels it on to wherever we're going to show long-term memory. What's there? So that's we want. You got to know that basis of what each part of the brain, what the frontal lobe does, what the occipital lobe, temporal lobe, parietal lobes, and we'll review that. And I had a little write-up on it that I was going to just put as part of this, but that's easy enough to come by. That was there. And so this is where they're beginning to look at it. So 3 types of ways it does this. So the communication is neurotransmitters, which we'll do a review of. Local mediators, those are those sort of in that generic category that originally described as prostaglandins, substances that are released locally and act locally. And so their speed comes from the fact that they're working on the same or tissue or cells that are immediately there. That facilitates, so they're not as fast as nervous transmissions, but not as quote unquote slow as endocrine system hormones. Okay? And so the local mediators are what we call the paracrine, para for next door to. And so and again, fast or slow signal is sort of the same thing with its effect. Fast signals have rapid effects that will go away rapidly. Slow signals go away more slowly, so by definition, they're longer acting. Okay, and then the specificity, whether it's general or that's something we get to sort of on an individual basis. So as you can see, they generalize, and for taking a test like the MCAT, most of your fallback position is what do they generally do? Like if you're lost on a question or not sure about it, think general. Read the question and see if it's giving you something specific or it's referring to something specific in the passage that's there. Nervous system, specific, fast, fleeting. Endocrine, okay? Endocrine, generally speaking, generalized, so they're slow and more sustained. Yes, there's certain ones in endocrine that go to specific targets, but there's many that are more generalized in nature. I thought somebody was trying to define me there. And they give you the paracrine lying somewhere in between. Okay, and the same thing. Neurotransmitters, short distance because they're just between cells that are effectively adjacent, whether it's a neuromuscular junction or a nerve to nerve junction. Local mediators, immediate area, and then the hormones have to go through the bloodstream that are there. So all of those are the anatomy as well as the physiology, and they're giving you this idea. Somatic nervous system, neuromuscular junction being that, or nerves leading to the neuromuscular junction. Very, very rapid, most rapid we have. Autonomic, a little bit slower. Remember, there's more. So here it's almost all myelinated fibers. Here it's almost all non-myelinated or limitedly myelinated fibers. Here they're not using nervous system fibers, and the endocrine are also not using it. So it gives you sort of an idea going from specific to general and speed. So it's not a bad graphic to sort of cement back here. There. And so and they told and these I find these little side things to be good. That are there. And here they're trying to give you the modernize this slow into the endocrine like a letter, you know. How they came up with the term snail mail, I don't know. They've come up with that. It takes a while to arrive at it. Like, well, last I got a lot of junk snail mail. And fast and fleeting is more like a short text. Not like that. So all the different things here, you say, yeah, roles in homeostasis is part about it. And so I mean, here they're referring whether they're doing the physics. These are different. If you get the exam crackers sequence, which are relatively inexpensive and probably worthwhile. I mean, I'm sure I'm not supposed to be photocopying these and giving to you, but for the purpose of education, we do that. But I don't think they're overly expensive. If anybody sees me photocopying, I kind of copyright infringement. So this is interesting. And it's almost like background noise. We are constantly, you're constantly aware of what's going on. I mean, you have the best context to see it through yourself. I mean, I look around the room, what am I seeing? I might see something, notice something, I know that periodic table sits over there, it hasn't moved, it's not folded, it didn't fall down. I mean, we heard the noise before, so I glanced back in the back, and all of a sudden I'm registering. It's not a big deal. So, it's not so cold or uncomfortable that I would go back and close the window, but the window's open. The noise factor might be there. I can see one of those monitors is flipped. We used to have monitors in the back that were there. I mean, those are little things. To me, it's, do we respond to this or not? That's kind of what your nervous system is. It's filtering all this information, and then it goes back to this idea of fire or not fire that goes on. So it selects the most important information based on experiences, any preconceived ideas. Sometimes they're instinctual. I mean, I can tell that when the cat hops in close proximity to the dog, there is a response. I don't know why. We're having some serious cat and dog issues. And so all of this, so it's, again, conscious perception is a significant part of the nervous system. So a lot of the homeostatic regulation that we have talked about, what our nervous system does, is really not something we have to be concerned ourselves about. So it's unconscious regulation. Okay, very simpler processing mechanisms go on. So when we talk about those things, sodium level goes up. Maybe it involves aldosterone. Maybe it involves something in the kidney regulation, or it goes down. Blood pressure. Well, it's just our presets, and we're staying around them. That's really all it is. So it's not something that, the fact that you have so many different areas sensing calcium levels and potassium levels, we adjusted them accordingly without, you and I don't have to necessarily do it unless it's a significant problem. And again, most of the medications that we take and in medicine are ones that impact when the homeostatic mechanisms are out of balance. Typically, most of the medicines impact the autonomic nervous system. Why am I taking calcium channel blockers for high blood pressure? Because my high blood pressure is high, and for whatever reason, it's not so much that I have high calcium, I'm just trying to retard the level of extracellular calcium so that it doesn't adversely impact my smooth muscles controlling blood pressure by way of the sympathetic nervous system. It sort of moderates their effects. That's where a lot of the medications come from. That's useful information to remember as well. Okay. Sensory information, different forms, impact from the environment, internal and external, physical information, absolutely part of it. Length of the neuron, chemical signals required to pass it. So it's, again, an electrical system mediated for the most part by chemicals. Is there direct electrical contact? Yes, mostly in the brain. Where at most of the time that direct electrical contact are modifiers. Okay. Think of that being part of adaptation. Little modifiers are saying, I'm going into a loud environment where there's a lot of background noise, and I put that aside, ignore that. Or I'm going in the lab and somebody's been working with cultures and they're fermented, and that, and you have the olfactory adaptation. So whatever sense is involved that are there, that's where most of those electrical connections are modifiers. Pay less attention to that, electrochemically speaking. So, and again, the chemical signal is basically the way, and again, I phrase that always as the rate determining step. We give that a certain degree of specificity. What chemicals? And again, remember, unlike the neuromuscular junction, where it's only acetylcholine, most nerves in the brain, certainly, and the rest of the central nervous system, depending on what pathways are involved and the nature of the signal, can secrete more than one neurotransmitter. So they might secrete something that's excitatory or one thing that's inhibitory. Remember, that's the whole ball game. Neurotransmitters from nerve to nerve, have one conversation, fire or don't fire. They're either excitatory or inhibitory. They'll create something that's going to be a depolarizing signal or a hyperpolarizing signal. Again, in one in and of itself will not create an action potential. It's about the summation, how rapidly or how many over a short distance area. So all of that stuff, the generics of that. Neuromuscular, it's all about, it's every signal says fire, it's a question of whether we reach threshold, whether it's over time or over an area, whether it's the frequency of the signal or the amount of receptors that are triggered. So either temporally, what they would call temporally, or spatially. The same is true here for the central nervous system, except it's a little bit different because it can be either fire or don't fire. We're not limited. Okay, so all of that is part of it as well. Sensory information, input from the environment, as we said, physical information, travel the length of the neurons, the synapse, which they cover later. The nervous system, this is the part where I kind of was going to talk about. It's, to me, spinal cord nerves and support cells are something that are part of it, but less about how it works. To me, the spinal cord is just an extension that's there, and the nerves that emanate off of it, other than the ones that are doing autonomic functions, basically maintaining homeostasis, really everything else is just relaying signals. It's either signals to fire, to move something, to do something, or bringing in sensory signals. That's really all it is. It's there. Obviously the big problem is it's damaged, or it's impinged in some way, like, my back axon. And so all of those structures, it's the parts of the brain that I know they will have an interest in what they do. And, I wanted to go over that summary because we did it in anatomy, and it's a bit of a time. We're talking about a good 6 months ago when you and I covered it together about that. So the brain and spinal cord make up central nervous system, which everything else that protrudes from it is peripheral nervous system, which already. The overall organization they discuss later and in greater detail. 5. That's an interesting way they describe it. Processes the image, enhancing certain parts and deleting others. So I guess it's like our brain's like a Photoshop program. I don't know. I've never used it, so I don't know. So here's the electrochemical part. Crucial to understand how it works at different levels. Most important level is cellular, at the neuron. Then at the organ, the synapse between a nerve and whatever its target is, and in the system itself. Okay? Those are the key areas. So they're telling you what you really need to know. And I agree with all that. So understand what a neuron is. And they made some very interesting points about this. So whatever your view, when you draw any kind of generic nerve, so you have what they call the cell body or soma or nucleus. But we don't use the term nucleus. Again, we use different terminology because nucleus is an older term. It's already associated anatomically, not with the individual nerve cell or neuron, which this is. And even though there's variations of different, one they're going to ask you about is the typical dendrite or receptor. And then the axon, which is this whole big thing here, and transmitter. And obviously each of the immense amount of branches that each of these have. So cell body or soma, terms that you can see work, and this area where the signal is, where effectively we process all that information to determine whether or not we're going to get an action potential. This little hillock, this raised area where the sensors are, the axonal hillock. The interesting point that I noticed there is proximity. Again, it's KISS, keep it simple, stupid. The dendrites, inevitably, in a typical neuron, are very close to the cell body, but moreover, close to where the signal gathers. So there's not a lot of deterioration, whether it's saying fire or don't fire. The long journey is down the axon, but once we basically achieve action potential there, proceeding and eventually releasing here where the neurotransmitters are released. We're looking at the classic model. So that you need to be familiar with. And so that I found that, so I was trying to think of the things that I thought were points of emphasis. And he's trying to explain this because I know it's more or less a review passage. So the physical structure of the neural mechanism as it passes the signal, again, fast and fleeting and specific. The long axon, contact with the specific sites, okay, that are there. And the slowest, the chemical portion in that tiny space. Again, how slow is slow? When you're talking about something that conducts a signal, 100 to 200 meters per second in a myelinated nerve, you and I would hardly consider that slow. But again, the analogy is talking to somebody on the West Coast in real time, or having a streaming service, basically streaming it to you in real time. I'm watching, soccer in England yesterday, okay, more or less in real time with a minimal amount of delay, okay, and, how long it would take a plane to fly, the hours that it would take. It's the difference between an electrical signal. And so there is a certain slowness, if you will, and that's where, again, where does modern medicine try to impact all of these things? At the synapse. That's the critical piece. That's the secret sauce. It's very Big Mac. One of my early jobs was, we always start working in food, was at a place called Geno's, which doesn't exist anymore, which tells you how successful. McDonald's had just opened. This was 1967, 68. They were just starting to make their way here to the East Coast, New Jersey, and very famous from Baltimore, named Gino Marchetti. He was an all-world defensive end for the Baltimore Colts, the Johnny Unitas heyday Colts football. And Gino opened a series of Gino's restaurants to compete. And interestingly, they had the KFC franchise in them. They had a contract with KFC's. So that was one of my early jobs. And they had a Gino Giant, which was the same thing as a Big Mac to compete with it. And you knew to say I was on them. Most kids start working with food. So all those types of things that are part of it. The neuron, okay, obviously no longer is amitotic. This was interesting. Uses facilitated or transport to move glucose from the blood into its cytosol. So it's not dependent on insulin for this transport, unlike most other cells. So it's effectively almost entirely upon glucose. That's the big number. Why? Remember we talked about that in endocrine, in diabetes. What is so dangerous about taking your insulin for a diabetic and not eating is it can rapidly lower available glucose. And if it lowers below like 50 in the bloodstream, that's when diabetics will just black out. And if you don't, that's the immediate risk of death, as opposed to high blood sugar. You might feel sluggish, you might not feel right, but you're not going to be driving a car and all of a sudden black up. And I told you all the anecdotes about all the diabetic patients. This is why. Okay, the insulin has nothing to do with getting it. The brain needs glucose. And it goes in by facilitated diffusion. I found that to be very interesting. And that was a point I probably should have made. And the reason I didn't make it, I didn't know it. Okay? And that explained it very well. Facilitated transport, not not insulin dependent. The neuron depends heavily on the efficiency of the aerobic respiration. However, it is not able to store significant amounts of glycogen and oxygen. This must rely on the blood to supply those resources. And it's the old story. I mean, in the absence of oxygen, 3 to 6 minutes, brain cells start to die. And when brain cells die, they're dead. They're sleeping with the fishes. Done. Moored. Taking a dirt nap. You know, that's my pet peeve. We never say something. Oh, yeah, my wife's mom died. She's 98 and a half years. I didn't say passed away. Where'd she pass to? Was she taking a test? I know, it's easier. That's why I was showing a picture of my mom and dad to Dr. Hillwood this morning because I was trying to find a picture of my sister because we were chatting about some stuff. And like, I get teary just looking at it. Okay, but they died. Me first, my dad would have been 111. He's not going to live that long. I'm over it. Not a lot. Just saying. I mean, my mom will be gone for 14 years. You know, you gotta get past that. All right. Stein's pet peeve. Didn't mean to my neuroses on top of yours. Okay. So neurons in different parts of the body, different physical appearance, fine. We're doing the basic anatomy. Dendrites, the physical appearance of these parts correspond to its function. Dendrites, short and stubby, okay? Many dendrites, many branches, inputs from many neurons. So it's all of it. And summation, again, what they're basically talking about, fire or don't fire, can be spatial, over space, or temporal, as we do over time. The utility of summation is particularly evident in gathering of sensory information. That's an important point. It's our ability to ignore the background noise and respond appropriately. You're in the car, you're talking to somebody, you're listening to the radio, maybe you have, maybe you're listening to a podcast, whatever. That type of stuff. How you can tune that and still have whatever senses. I realize I'm going to have to prioritize what I'm seeing and to a certain extent what I'm hearing was abnormal and how we're able to do that. So since the intensity of the stimulus can be coded by frequency as well, and a stimulus of a higher intensity will be more likely to trigger an action potential than less. It'll be that the flashing lights, the sign, all that, vehicle in front of you stopping more rapidly than you anticipate. Then now, this is, and I didn't do justice anatomically with my horrible artwork, the small size of the dendrites, quick transfer. That to me was an important point. Okay, the cell body contains organelles of the neuron, including the nucleus. Okay, typically the cytosol, highly conductive in that area. They create disturbances in the field that are transferred immediately to the hillock. So it has to do with anatomical construction. There's not a whole lot. That's there. Highly conductive, short trip to make it. And then if it's large enough to generate that voltage strain, okay, the action generates action potential in all directions. Okay, so when they say all directions, again, we talk about the all or none phenomenon. I mean, there's anatomical reasons behind that because the area preceding it. I mean, again, the point that I made, and I don't know, Lindsay did, Dr. Hill would talk about inactivation gates on sodium voltage gated channels or not.
Well, like how action potential.
Yeah, actually, but you talk about the absolute refractory period.
Like the graphs and stuff.
Yeah, I mean that, and a lot of that is due to something called an inactivation gate. So understand there's a certain, even though that signal is going in all directions, it's limited directionally to go down the axon and to go down, those the internal neural tubular channels that are there for the purpose. They conduct the impulses in one direction. They're bi-directional for chemicals and resources when they undergo things like reuptake. So she did that. She did metabolism and reuptake. Good. See, I've taught her well. That's because she's doing neuroscience. She got roped into that because her husband was, used to come here and do that, but it's such a schlep to be teaching that in Greensboro. And then he would do that in the evening. Did you meet Mr. Dr. Hilwig? Oh, Matt's a nice guy. Very nice guy. So, does not contain enough ion channels to sustain an action potential. The axon, however, carries an action potential to the synapse, etc. The cell body doesn't have the channels. It's the axon that has the channels, the point they're trying to make. That's there. Okay. Some axons are very long. Again, a meter or more, like I said, 6 foot tall person. Somebody like a basketball player taller than that. I mean, to two nerve circuit to get to your big toe, from your brain to the lumbar sacral area, and then from lumbar sacral area down the whole lower extremity, close to the big toe. That's a couple of long nerves for that two nerve circuit, so to speak. So the answer is having a single axon minimizes error and maximizes efficiency. Okay. And multiple synapses would provide opportunities for information to be transferred, and slowing it down. I mean, just think. The example, you're driving a car, hitting the brake. I mean, you don't need to, hey, hit the brake. My kid was telling me, oh, he was pissed. Okay. Because he had gotten his truck to move his RV down, which he's living in, down to Florida. And I mean, the truck just upped and died on the highway. He got nearly rear-ended. That was last week. I didn't hear from him a couple of days. One of two things happened. Either something was wrong, which was the case, or he met a new lady friend. And, time sort of lost its meaning for a while. So, again, by contrast, ion channels allow the ions to travel from one side of the membrane to the other. Different ion channels specialized in terms of which ions allowed to pass through, blah, 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 blah. Some of the receptors are themselves ion channels and open in response to binding a ligand, which we are already familiar with. So the basis of this system, you remember, when the neurotransmitter, let's assume it's excitatory. The neurotransmitter is released. It has a depolarizing signal, bringing it closer to threshold. Typically, let's say it bonds to a ligand or chemically gated channel on the dendrite of the subsequent nerve, opens that up. Let's say it allows sodium to come in, potassium to go out. Again, the 3-to-2 relationship continues just like the neuromuscular junction. 3 sodium going one way, 2 potassium going the other way. The net effect is more positive or less negative, bringing it closer to threshold, and it summates either temporally or spatially, and we get a response that's there. And so, I mean, all of that is important. So it's in addition, ion channels vary in how they open in response to different electrical potential. Some receptors are themselves ion channels in response to a ligand. These receptors are crucial because those are the ones that really, typically the chemically gated channels, and they'll look further into it. And again, depending on the channels and the pathway, this is the electrochemistry stuff. And so I can't do it justice. Property of all neurons along with features surrounding environments carry out their function of transferring information through the nervous system. Okay, they'll look at how it, but first understand how the neurons generate voltage. Who you have this week? You have Buxton. Ask him. He can reconsider vaulting, or what I call revolting. There was a great series on Prime, not a series, there was like a movie, like a documentary on Prime, all about the Three Stooges. Yeah, you're revolting, no? Join me. So, three nice Jewish boys from the Lower East Side, the Horowitz brothers. That's they came to Howard. Sam, Moses, and Jerome. Shem, Mo, and Jerome became, who had curly hair but always shaved it, became curly. If you didn't. Okay. Insulating membrane, that's the myelin, and it's sometimes more, sometimes very little. Okay. In the case of a neuron, the two solutions are intracellular and extracellular. You knew that. Okay. The two most important ions, sodium and potassium, that's every cell. The unequal distribution, okay, much higher extracellular sodium, reverse is true for potassium, we knew that. And this sets the resting potential typically about -70. And again, the reason is this large preponderance of potassium leak channels as compared to sodium that are there. It's just the nature of those channels that are such. And the other thing was very interesting. As the potassium gets close to the internal membrane, what it's doing, because what neutralizes the potassium is the anionic portion, the negative portion of the proteins. The reason why it's so negative, so close. Remember, it's not the interior of the cell, which is effectively neutral, or in the extracellular fluid. You're pulling that negative portion of the proteins closer to the membrane. How's that? And by the same token, that's not existing on the outside. The sodium is getting pulled closer. That's what, and that was a very interesting comment that they made about this. So the resting potential or voltage is the same as the voltage described in the context of electrical charge. They talk about that Nernst equation. I don't want to get anywhere near that. So that a sufficient disruption, read that as threshold, is what able to generate cascade of events that continue as an action potential. Okay? And so if a neuron loses the ability to establish the resting potential, it can no longer get. So to have action potentials, you have to have a resting potential. And for whatever reason, there's a physical or mechanical, chemical damage to that nerve, and it can't get to a resting potential, you have trouble. And so potassium out principally, okay, as the ion approaches its chemical equilibrium, inner outer surfaces, etc., etc. There's many more channels allow diffusion of potassium as a result. Okay, as potassium diffuses, okay, and we get to effectively everything goes through equilibrium. Factors that cause this gradient are the diffusion of positively charged ions here, and the negatively charged substances along the inner side of the membrane. That is the the negatively charged anionic component of the proteins. In the extracellular environment, discouraging the movement of more potassium ions out of the cell, okay, negative on the interior. The combination of these opposing gradients creates the electrochemical gradient of potassium. And so when they talk about electrochemical, again, you have the electrical basis, the positive and negative, and the chemical aspects that are there as well. The buildup of the negative charge along the inside of the membrane occurs as a side effect of the diffusion of potassium. The potassium ion solution associate themselves with the negatively charged R groups of proteins within the cell. They all start to move toward the membrane. They drag along the protein. The protein could move, it would, but it can't. Proteins are much larger, they just barely get through. So the positive charge buildup along the outside of the membrane as potassium ions flow out of the cell attracts the negatively charged proteins, causing them to stay in their position. Other anionic substances, chloride, contributes to the buildup of the negative charge. And so that's one of the factors that helps to create that gradient. The membrane, the way we teach it is typically, we forget that the sodium potassium pumps are continually active. Just when there's an action potential, they become excessively active. So the sodium potassium pumps functions to maintain or reestablish. We know what the potassium does. We know about the 3-to-2 relationship, etc., etc. That's part of it. The resting potential stays constant, but understand it's working actively, even in the absence of any action potential. And here's the Nernst equation thing. So this is on you. I'm not doing it. The MCAT requires understanding the variables of the Nernst equation, what happens when temperature is constant, what they all stand for. I don't know. So enjoy your Nernsting. Ask him. I'll buy it more than one. Unfortunately, that's physics. So it says that other ions also have concentration, but they do not significantly affect resting potential due to low permeability. So it's all about the potassium. Many potassium channels compared to number of open channels over the resting potential. Some leakage of sodium, we know about that, bringing it back. The take-home message. Most importantly, it's set up by diffusion of potassium. Potassium diffuses out of the cell, dragging the charged proteins that get stuck on the inner side of the membrane. When the chemical gradient of potassium equilibrates, the inner side of the membrane is negatively charged compared to the outer side. The resulting potential is very close to the equilibrium potential of potassium. Another thing, understand the Nernst equation and its variable. I think we will stop it here, and I'll get that other stuff in order afterwards. And here's the other thing, just quickly. Unlike wires, why it's different. The membranes of the axons are fat. They don't conduct electricity. So it's about the solution inside the cell on opposite sides of the membrane. Okay? And so the action potential is the evolution of this problem. The signal will be transmitted down the axon as fast as the ions can travel and channels can open. So it's it's interesting, a revised wire where the traveling of the ions rather than the electrons is the part of it. And they talk about things like drag and things like the physics guy next door. All right. Thank you, everybody. See ya. And I'll have more.